How did a team of engineers build the world's longest sky gardens, 156 meters above the ground?
It must have been incredibly nerve-wracking. They had to be so careful.
What do you get when one of the world's most radical architects builds a railway station in the path of two natural disasters?
Building in earthquake zones is enough to make anybody, any engineer, nervous. But building in the shadow of a volcano?
And how is the world's most slender tower strong enough to survive winds of over 50 miles per hour?
Tall structures are prone to move. They're particularly vulnerable to wind. So the thinner they are, the more serious the threat.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? In a tiny pocket of downtown Singapore, the challenge was set. To create a development of almost 2,000 apartments, where before it had been home to just 342. But on a site so small, engineers had to think outside the box. It could have been another boring tower block of identical floors and flats. But designers and engineers excelled, creating the tallest public housing residential building in the world, the Pinnacle at Duxton.
This building is a spectacular achievement on a site that most developers would have just walked past and not even given a second look.
A stunning 7-tower, 50-story apartment complex with 20,000 square meters of outside space. But not on the ground. Engineers did it by building the world's longest sky gardens, 156 meters in the air.
It's an amazing feat of engineering, but obviously there are going to be some risks that come with it.
A plot too small to build on conventionally. Thousands of prefabricated concrete panels, light enough to be lifted, but strong enough to support the 50-story towers. And sky bridges that were too heavy to be craned the 156 meters into the air. Just some of the complex problems faced during construction. So how did they build it? Like lots of cities, until recently, downtown Singapore was home to the financial district, but practically no one else. Keen to reinvigorate the area and attack the lack of affordable housing, the government launched a design competition to redevelop a tight and difficult plot. Architect Peng Beng's design was picked from over 200 entries.
The two main aim of the Pinnacle at Duxton was to really inject new life into this neighborhood and also to increase the population density of this area.
The plot was slightly larger than 2 football pitches and had been the site of 2 10-story residential blocks housing 342 apartments. The government's plan called for at least triple that on the same space.
The other huge consideration when you're building mass housing like this, where people are so densely packed together, is how do you make it pleasant? How do you make it a place that people actually want to live in?
The answer lay in a design that would push engineers to their limits. In a bid to increase capacity, while also creating attractive, comfortable homes, Peng and his team drew up a scheme that would become the world's tallest public housing residential buildings. Packed into the awkward question mark-shaped plot would be 7 163-meter-high towers. Each would be joined to the next at the 26th and 50th stories by 6 enormous sky bridges. 20 meters wide, these bridges would provide 20,000 square meters of greenery and outdoor space for the residents to enjoy. And with each measuring 500 meters long, they'd create the longest sky gardens in the world, if engineers could work out how to build them.
So the key question here is how to get the maximum amount of usable space into what is quite a small and irregular plot. And what they've done here is they've arranged the building so as to kind of weave through the plot, just to really get as much into the available space as possible.
As construction began in 2005, the site threw up the first of many problems. There wasn't enough space to build the towers using conventional methods, and there was only one small access road in and out.
The site was so tight, it was so small, plus it was in the CBD area, the Central Business District area, which meant that, we would cause havoc and traffic jams during construction.
Already crammed with materials, heavy machinery, and hundreds of laborers, there was little space left. Casting the 50-story concrete towers on site would be impossible. The solution was to prefabricate off-site.
Using prefabricated technology was very important because the site was so crowded.
90% of the structural elements would be prefabricated in a factory 18 miles away. Then each piece would be transported to site. Instead of seeing this as a problem, the engineers turned it into an opportunity.
Sometimes when we do prefabricated, it's just a facade panel, but in this case, we designed the structure, the beams, and the columns into these panels so that as they were being put up, the structure was also being built at the same time. And the rainwater downpipes were installed into the panels that would drain water from the balconies and from the roof.
So, prefabricating the building off-site would overcome the issue of the small plot and allow Peng to hide away some of the services within the hollow walls. But it also created its own unique set of problems. Normally with a tower block like this, the concrete would be poured on site. It's the cheapest and most efficient way of ensuring the structure with its central support columns of concrete and steel is strong enough to brace the building. How would they be able to prefabricate concrete sections that were strong enough to bear the forces of these enormous towers, but also light enough to be lifted into position by the tower cranes? Coming up with a solution fell to the engineering team.
The tower crane capacity is less than 10 tons. And for such high-rise building, a lot of components are more than 10 tons. So what we have done, in order to reduce the weight of the component, we have developed a hollow core system.
Instead of being solid, these panels are hollow, making them lighter. They're also pre-stressed or compressed as they're being made, which makes them much stronger than normal concrete.
These panels are connected together in an interlocking way, just like a Lego block. And then we would put in high-grade concrete to seal up all the joints. So the joints would be cast in place, and when this cure, it would then act as a continuous unit.
Although building using prefabricated concrete is around 10% more expensive than pouring on site, in this case, it turned out to be a saving. Because although there were additional costs initially, the team got faster and faster at putting the towers together. Instead of taking 10 to 12 days, soon they were building whole floors in just 6.
It just illustrates that to make a building like this, you really have to approach it from a completely different way of thinking.
The next problem the team had to overcome was to ensure the 1,848 apartments didn't seem identical on the inside or out.
Part of our challenge was to use this way of construction, but produce something that looked totally unique and as if it was impossible to be fabricated off-site.
The solution was surprisingly simple. They created 5 different styles of facade panels. then mixed them up. So as you look at the exterior of the 7 towers, the frontage appears random. In fact, it's anything but.
So you actually have an interesting facade, and at the same time you give the buyers and the residents a choice of units. So you can pick a unit with a balcony and you can buy that unit instead of having everything all uniform.
That idea of uniqueness doesn't stop at the front door. Prefabricating the towers gave the designers another great opportunity, which would allow the occupants to make each flat their own, but also to future-proof them for when the residents' lives change.
If we could create opportunities where people could make something unique out of their own units, and they could feel like, you know, they were part of the whole growth process, and the building didn't start to restrict you, but it started to give you a sense of freedom, a sense of choice.
So how do you build cost-effective tower blocks of affordable housing, whilst also creating apartments that can be radically changed without radical building work?
In a typical high-rise, the columns and structure would take up quite a lot of space within the units. So we thought that if we pushed all of this structure onto the periphery of the units, the walls could then be easily taken down, so that if you wanted to, you could tear down all the internal walls and you can have just one huge apartment.
So by building all the structural strength into the flat's exterior walls, everything inside can be moved or even removed to open up endless possibilities depending on the needs of whoever's living there. And while each floor comprises of the same basic structural layout, the opportunity inside each flat on each and every floor is limitless.
Each of the floors is a variation of the same plan, and with that variation, you have individuality.
The next major challenge came in 2009, when the 7 tower blocks were ready to be joined together to create one interlinked scheme. On the 26th and the 50th floors, a series of sky bridges would connect one tower to the next, creating over 20,000 square meters of outdoor space for the residents, high up in the sky.
We created additional communal spaces in the air, which is actually at the sky bridge level. So we actually multiplied the amount of communal spaces available.
The residents now enjoy the world's longest sky gardens, but to put these huge links between the towers would be the biggest challenge yet for the engineers to overcome. Made up of giant steel trusses topped with concrete, the heaviest bridge weighs 350 tons, the equivalent of a Boeing 747. So how did they manage to get the sky bridges over 150 meters in the air?
It's no joke trying to get 200 tons of steel to the very top. They couldn't use a crane.
10 years ago, tower cranes couldn't lift such heavy loads, and the site was too cramped to bring in bigger ones. So the engineers came up with an ingenious solution.
To bring the bridges up to the correct location, we have to adopt a hydraulic crane system.
At the top of the 2 buildings where the sky bridge was being lifted between, there was a hydraulic jack connected to a winch.
Each sky bridge was attached to steel cables and then lifted into place using 4 hydraulic jacks and winches, 2 on each building. Computer-controlled, they all moved at exactly the same time and speed to lift the sections into place.
It must have been incredibly nerve-wracking. They had to be so careful.
If there was any wind at all, they'd have to stop and tie off both ends of the bridge. It took 10 hours to lift each bridge into place, completing an extraordinary piece of engineering, and in the process, changing the way the residents would live.
At the sky bridges, we have communal gardens, we have jogging tracks for the residents, we have play areas, and we also have elderly fitness stations, and we also have breakout corners, little gardens where people can sit down and chat with their neighbors.
Construction was finally completed in 2009 at a cost of over $205 million. The end result is amazing, a complex that serves the residents' every need. Neil Kim Powell was one of the very first people to move into the Pinnacle and has been here for 10 years.
Yeah, this place is unique, but it's pretty clean. It's very convenient. Everything is just a few steps away.
Over 5,000 residents from every walk of life live here. Now this vibrant community enjoys these sky-facing spaces high above the hustle and bustle of the city. A tourist destination, thanks to its stunning views. The Pinnacle at Duxton has successfully injected life into this district, and 10 years on, continues to be a model of world-class public housing.
The Pinnacle at Duxton is amazing. It's like an engineering magic trick. It's wizardry.
On Britain's south coast, the city of Brighton, like many English seaside spots with its piers and seafront, has been trading on its Victorian past. But in 2006, Brighton decided it needed a new, state-of-the-art landmark attraction to bring the city into a new century and millennium.
It's something that's going to have to really be built to stand the test of time.
It took 13 years of planning and would challenge both architects and engineers.
It's right on the edge of the possible.
But the results would be an extraordinary and innovative vertical pier that would allow visitors to walk on air.
It looks a lot like an amusement park ride. Like it's supposed to be spinning or something, moving up and down really fast.
As well as being a marvel of modern engineering, the i360 is also the world's most slender tower. A £46 million landmark that whisks 200 passengers up to a height of 138 meters in the face of buffeting coastal winds. Constructing at this kind of height, where even cranes couldn't reach, engineers had to think outside the box. So how did they build it? The jewel in Brighton's seaside crown was once the West Pier. It had been the finest Victorian pier in Britain. But throughout the 20th century, it had fallen into disrepair. And then in 2003, it was all but destroyed by an arson attack. Brighton Council were on the hunt for a must-see attraction that reflected the original pioneering spirit of the West Pier, but with a 21st century twist. Meanwhile, 60 miles away, the architectural wizards behind the iconic London Eye, Julia Barfield and David Marks, had come up with a new and exciting visitor attraction that they thought would be the solution.
The success of the London Eye was such that we got approached by many people wanting to replicate it. And so we kind of looked at what was the essence of the London Eye. And we then looked at how we could replicate that experience in a different form.
David and Julia's design for the i360 would see visitors rise up into the sky to get a panoramic peek at the breathtaking surroundings. It was decided the perfect spot for it would be in the shadow of the remains of the old West Pier.
It is the site of the original West Pier, which is one of the only Grade 1 listed piers in the country. It was one of the most innovative piers in its time, and sadly it burnt down. So it was like the phoenix from the flames, really.
The final design for the i360 would be a world first, as well as the tallest structure in the whole of Sussex. The 162-metre tower is made up of 17 stacked steel cans that get taller and thinner as you go up, held together by 1,336 bolts, weighing a combined 30 tons. The 900-ton tower supports an 18-metre wide toughened glass and steel pod, that's 10 times the size of a London Eye capsule and can hold up to 200 people. It uses state-of-the-art cable car technology to drive the pod up and down at less than 1 mile per hour. Construction started in June 2014 on the beach, meters away from the sea. A tower of such height and weight would put enormous pressure on the base, so its foundations had to be super strong. But the engineers would first need to construct a stable area to build them on. Dr. John Roberts, who'd been chief engineer on the London Eye, was tasked with the job.
So what looks like shingle here, looks like the beach, in fact is just covering up the concrete. So that's actually the top of the foundation, the concrete is just there.
It would take just under a year to lay the foundations for the tower. The first stage was holding back the sea.
We're about 3 meters below ground level here, and the concrete foundation is 3 meters thick. So we had to dig an excavation more than 6 meters into the beach from the beach level. As you are aware, we're right on the edge of the sea. So when you dig below sea level, you usually come across water.
The team drove in concrete piles around a 24 square meter area of beach, and then started to excavate 7,000 tons of shingle. On hitting sea level, they had to pump out the water day and night until they reached the chalk bedrock over 6 meters down. Only then could they begin pouring the 4,000 tons of concrete.
We had to use concrete coming from every concrete plant in the whole of Sussex. I mean, this was one of the largest concrete pours that has been done in this area for many, many years. It was done in 2 halves, and even then, each half took more than 30 hours. You have to have a supply and you have to have a backup in case the supply goes wrong, because once you start, you can't stop. So in fact, nobody else in the whole of Sussex could have any concrete at all on those 2 days.
In 2015, with the foundations in place, the team made a start on building the main structure. Comprised of 17 gigantic steel cans, totaling 162 meters in length. Each of these steel cans or tubes differed in size and thickness and had to be carefully tailored according to where they appeared in the tower structure.
There's very few places in the world where they can be made. So the tubes were rolled and welded together in a special rolling machine in the south of the Netherlands.
It took over 18,000 man-hours of welding to make them, before being sailed by barge from Rotterdam across the North Sea, arriving right in front of the construction site.
You can also see here with this hole, this is a hole through the tower, and you can see how thick the steel is in the tower. This is 85 millimeters thick steel, and this is the bottom section. This is can number 1, the one that sits on the ground, of the 17 cans that make up the tower.
They may have got them there, but the next problem was how to put them on top of one another.
The big problem when you're building tall things is that the maximum lifting height of cranes is 100 meters or about 330 feet. The i360 is over 500 feet or 160 meters.
So how do you build something that's taller than the maximum lifting height of a crane? The ingenious engineering solution was to build from the top down. A temporary 60-meter-high jacking tower was fitted over the spot where the i360 would go. Then the steel can that would be the top of the tower was put at the bottom and lifted up by the 16-ton collar just high enough for the next can to go underneath. These two would then be bolted to one another before being lifted again.
So if you put number 17 in first and lift it up, and then put 16 underneath it and put the next one underneath that, you can build it that way instead, and you don't need a crane.
This procedure would be carried out again and again until the tower reached its maximum height of 162 meters.
The very last operation to put the last piece in at the bottom, the tower that you were picking up weighed 1,000 tons. So you had to lift 1,000 tons into the air to put the very last piece in at the bottom. It was done in just 10 weeks from start to finish.
Now they had to make sure it stayed there, despite being in such an exposed location and being battered by winds of over 50 miles per hour.
Tall structures are prone to move. They're particularly vulnerable to wind. So the thinner they are, the more serious the threat.
At 162 meters high and 3.9 meters wide, the i360 is the world's most slender tower.
So you can imagine that when the wind blows, the structure vibrates. Think of it like a guitar string.
This phenomenon is known as vortex shedding, where turbulence caused by the wind hitting the tower causes it to vibrate. Unchecked, these vibrations could induce motion sickness in visitors and even cause metal fatigue in the structure itself. So John and his team devised a solution. They would add a 5mm thick aluminium cladding with a special finish to disrupt the flow of the wind.
The cladding has been perforated and deformed in a way that stops the wind blowing smoothly around the tube of the tower. And it's done to prevent vortex shedding.
It was time for the team to turn their attention to its crowning glory, the 18-meter-wide curved glass pod that would take 200 people up into the sky.
The point of this clever engineering is an observation tower that stands completely safely in a blustery and highly populated spot overlooking the English Channel.
The pod would need to be strong enough to carry passengers and survive all weather conditions whilst offering 360-degree panoramic views of the Sussex coast. The glass would not only be key to the view, but also play a major part in the pod's structure and stability.
So instead of glass just being added on as a window afterwards, the glass is a glass and steel structure, and it doesn't have any bracing.
Yeah.
The glass is bracing the structure.
Yeah.
It's an extremely strong shape because it's curved in all directions. It's curved around the side. It's curved in all directions, and curvature gives strength, so it's a very strong shape.
Manufactured by hand in Italy, the toughened glass sections were sent to France, where they were assembled to ensure its complex geometry fitted together perfectly before being shipped to Brighton. In January 2016, the last pieces were put in place. Now it could be hooked up to its power source underneath the tower.
This is the machine room of the i360. This is the heart of the project in terms of making the pod move.
The 94-ton pod is connected to an 80-ton counterweight inside the tower by 8 steel cables. Raised to the top by an electric winch, on the way down, it's much more sustainable.
The motor then operates as a brake to let it down gently, and the braking force regenerates electricity in the same device. So the motor becomes regenerative and generates electricity when it operates in reverse, and you get back a little over half of the electricity that you used on the way up.
After over 2 years of hard graft in all weathers, the i360 was opened to the public in August 2016 and has taken over 1 million visitors into the clouds. It set the standard for must-see city attractions.
The whole process was a huge adventure and something that has been really, really positive for Brighton. It certainly regenerated the whole of the seafront.
Fabricated in the Netherlands using German steel, Italian glass, trialled in France and built on the British coast, the i360 is an international celebration of innovative architecture and engineering combined. In Italy, in 2003, an ambitious high-speed rail project was proposed to improve train travel between the north and south of the country. At its heart would be a stunning new rail hub in Naples. A half-kilometer-long curve snaking over 8 new train tracks, a stunning, passively cooled corridor for millions of passengers to sweep through to its platforms below.
It's so perfect in all of its angles. It also communicates movement and action.
To create this ingenious building, engineers would have to work in the shadow of Vesuvius, the volcano that destroyed Pompeii and is still active. In an earthquake zone, to create a fearless architect's impossible design, and figure out how to keep the huge glass-roofed complex cool in the scorching Mediterranean summer sun. This is the Napoli Afragola railway station. So how did they build it? In the late 1990s, with train travel in Italy on the increase, it was decided 4 new high-speed lines, 3 regional lines, and a single local commuter line needed to be merged together at a new railway station 12 kilometers from Naples. It needed to be capable of handling an increase from 10 to 30,000 passengers a day. But this would be no ordinary concrete box. This station would raise the bar for stunning looks, passenger experience, energy footprint, and seismic resistance. An ambitious brief called for a trailblazing architect, Queen of the Curve, Zaha Hadid, who had most recently designed the jaw-dropping Antwerp Port Authority extension.
When Zaha Hadid designs a station, you know it's not going to be an ordinary station.
The first challenge was that pulling all the lines together like this would normally completely cut off the area to the north from the area at the south. Filippo Innocenti was the project architect.
Quite an ambitious brief. The area is divided in two by the presence of the rail. So as it often happens, the rail, it creates a barrier in between two sides. So it is fundamental to provide a clear connection in between the two sides of this area separated by the railway.
Zaha's solution was to create a huge 30,000 square meter elevated passenger concourse on 5 levels that would bridge over all the tracks and effortlessly link the north and south. 500 meters long and 44 meters wide, the steel and concrete structure would rise up 30 meters to straddle the railway lines. Built from curved poured structural concrete, the design was so complicated it would take 3D computerization to make it possible. The 5 floors would be covered by a 500 square meter glass roof, cleverly engineered to let the light in and the heat out. These windows would flood sunlight into the atrium in the center of the elevated concourse, which would be surrounded by restaurants and shops. The entire place would be cooled without an air conditioning unit in sight by creating a system of underfloor pipes filled with ice-cold water from the natural aquifers 80 meters below. Not only would this be a place to catch or change trains, it would be a meeting place for the local community and 30,000 travelers every day.
Most large stations have an entrance hall with ticket machines and cafes and shops to one side, and maybe an entrance hall next to the railway tracks on the other side. But here, they've put all of that on the actual bridge above all the railway tracks.
Construction on the €60 million project started in 2009, and the engineers working here had a constant reminder on the horizon of a clear and present danger.
In Afragola, we're quite close to one of the most important volcanoes we have in Italy, which is the Vesuvius, which is still active.
Mount Vesuvius is the only active volcano on mainland Europe. Its last eruption in 1944 killed 100 people, and the danger remains very real, with the potential to unleash the thermal power of 100,000 Hiroshima-sized atomic bombs. Volcanic activity isn't the only threat. The area is also at serious risk of catastrophic earthquakes.
The seismic area of Afragola is 3 in the range of 0 to 4, so still quite challenging.
Building in earthquake zones is enough to make anybody, any engineer, nervous. But building in the shadow of a volcano that destroyed Pompeii, yeah, you need to take that very seriously.
Builders made the 100,000 square meters of the station's exterior from 50,000 tons of poured concrete using formwork. This is where concrete is shaped using molds and reinforced by steel. Whilst it's strong and durable, it's also inflexible, making it more vulnerable to damage from earthquakes. If the engineers ignored this danger and created a continuous 500-meter concrete and steel structure, the station could fracture and collapse catastrophically in the event of an earthquake. But the engineers had a plan.
A more modern approach is to allow movement of the building. So in this case as well, where you have a number of flexible joints, what happens is it concentrates all of that movement at the flexible joints and then allows the movement energy to dissipate as heat. So it means that you get some movement there, you get some cracking as well, but you limit the structural damage to the rest of the building.
When you are exposed to seismic loads, these movements can be significant, can be in the order of 10 to 15, 20 centimeters, which means that the whole building has to be broken into elements, and this element has to possibly move one with respect to the other in the event of a serious seismic load.
They decided to divide the building into a sequence of separate zones, each no longer than 50 meters. And each zone could move independently by up to 15 centimeters. Tommaso Martellucci was the project's engineer.
These bridges, on the second, third, and fourth level, are connected at the hub with expansion joints that can absorb the stress and movement during seismic activity.
So the station was engineered to be tough enough to withstand an earthquake. But that wasn't the only force of nature engineers had to deal with. The design featured a continuous glazed roof to allow in as much natural light as possible. But here, in southern Italy, it would also be subject to the fiercely hot summer sun.
Building a glass structure makes a lot of sense when you have a lot of people that need to move through and it needs to be well lit, but that becomes a different situation when you're dealing with temperatures as high as 36 degrees Celsius or 100 degrees Fahrenheit.
So how would engineers overcome the challenge of filling the concourse with daylight, but cooling it in an eco-friendly way?
Naples can be extremely humid. There are days where the temperature goes really high and humidity is really unbearable. I have to say that I was quite nervous at the idea of having a building with a big glazed roof.
They needed a solution, because normal air conditioning would have come with huge costs, both to the budget and the environment.
What you're trying to do is to maximize the daylight that you can have inside the building and minimize the costs of the ventilation that you would have to fight against the solar heat.
Expert environmental engineers stepped in to solve the problem, using state-of-the-art technology based on ideas developed by the Romans 2,000 years before. First, they built internal shading fins into the roof, which filter the sunlight, holding heat above it and preventing it coming through into the passenger areas. A series of roof vents running the entire length of the station then allow the hot air to be funneled out.
The building is based on a mixed ventilation concept. It's combining natural ventilation together with mechanical ventilation.
On its own, this isn't enough to cool the concourse. The main cooling system is underneath the public area of the station in the service tunnel.
Here we are in one of the underground rooms at the heart of the plant that runs the station. One of the keys to the success of the building's energy sustainability is the air cooling and reverse cycle pump systems.
This passive air cooling system keeps temperatures down even on the hottest of days. Engineers drilled down 80 meters to access cold water from the natural aquifers running through the rock under the station. This is then pumped up and into a system of pipes similar to underfloor heating that have been laid throughout the station. But instead of giving off heat, the cold water absorbs it. It's then pumped back down into the aquifers, taking the heat with it.
A water source heat pump actually works very well in this situation. It's really good at absorbing the heat into the water and then running the heat out using the water as a medium. This was an idea that was actually developed pretty early on in the 1850s, but the first one actually wasn't built until about the 1940s.
In a world increasingly concerned about our environmental impact, these passive systems have come a long way, including creating the very coolest of chairs.
Within these seats, there is a system that allows hot or cold water to circulate and cool or heat the seats for the passengers.
Set throughout the station to allow passengers and locals to congregate, the elegant seating perhaps offers the perfect place to admire one of the most innovative uses of materials here. To cover the concrete surfaces inside and out, the designers wanted a smooth, weather-resistant finish that could flow over the building's ever-changing curves. They chose a material developed 50 years ago for domestic kitchens.
The outer skin of the building, as about 20,000 square meters, has been realized in Korean.
Korean is a brand of durable acrylic that most people might know from the kitchen worktops, but more recently it's being used to clad entire buildings.
And we were looking for a material that could be bent easily and to follow the simple curve of the building and to resolve the residual torsion of a number of areas of the facade. And the Korean was ideal for that because the continuous surface that allows to be bent at very low temperature, basically around 100 degrees, and can be put into shape very easily.
The panels were computer modeled and cut with 2mm tolerances.
Korean is made in panels and then they are bent in order to serve the purpose of allowing the curve of the facade. You basically treat it as wood panels. You can cut them and you can glue them perfectly without any trace of the junction between the panels. A very easy way of creating shapes with it.
In 2017, Napoli Afragola was finally able to welcome passengers onto its elegant concourse. For now, only 4 train lines are open, but by 2022, all 8 lines will be in service. This station will then be at the heart of the rail network in southern Italy, still keeping a low energy profile, but standing tall as a great example of how ambitious design and engineering can make life that little bit better.